This conference will now be recorded.
Hello everyone. So last day we ended with trends in their chemical properties, that is group 13 elements. Today we'll start the topic chemical properties. That means group 13 elements, how they react with different other elements or compounds. For example, water, oxygen, nitrogen, like this. And then uses of all these elements, individual uses. And after that, there will be some specific compounds related to boron and aluminium. That is the first two elements. There are some important compounds from the point of view of their application. So we'll also discuss that. So chemical properties, first we will see how these elements, they react with water. Reaction towards water, as you can see here, when it is pure boron, then there is no reaction with water and even with steam. So sometimes it may happen that with normal water, there is no reaction, that is at room temperature. But when it is steam, that means now it is greater than 100 degrees centigrade. So at high temperature, sometimes there may be reaction. But even with steam, if boron is in pure condition, there is no reaction. Only if it is red heat. Red heat means the temperature is beyond 450 degrees centigrade. Then only it can react with steam. Okay, so not just steam, it has to be red heat temperature, which is around, that is greater than 450 degrees centigrade. So it proves that it's not very reactive. Okay, so that is the next element, which is aluminium. In case of aluminium, now you can expect the reactivity a little more. There is decomposition when we have taken it in boiling water, and there is also evolution of hydrogen gas. Now this reaction is only possible if in the there is no oxide layer. That is, I am talking about the surface of the aluminium that we are trying to react with water. That aluminium, there should not be any oxide layer. Oxide layer is, oxide of aluminium is Al2O3. But there should not be any layer. Then only reaction is possible, because if this oxide layer is present on the surface of aluminium, then water cannot get in contact with actual aluminium atoms, and as a result reaction is not possible. So this oxide layer should not be there. Under that condition only reaction with water is possible, and after reaction we are getting here aluminium hydroxide, and there is also evolution of hydrogen. The next element, gallium and indium, they are not attacked by cold water or hot water unless oxygen is present. That means here we will not get any reaction, as we are seeing in case of boron and aluminium. So now the observation is different. Only when there is oxygen, presence of oxygen, then only reaction is possible. But here we are talking about reaction towards water only. So no equation we have here to show for aluminium and indium. Now the next one, that is thallium, it forms TLOH. Now see, in moist air it is forming TLOH. Here also oxygen presence is required. But one important point is, when it is hydroxide of aluminium, here oxidation state is +3. But when it is Tl, thallium, now the oxidation state is +1. So the formula for hydroxide is different. Now the formula is TLOH. It is not TLOH whole 3. Now the reason is inert paired effect. We know as we move down, the oxidation state +1, that is more prevalent in case of the last element, that is Tl. So that is why here we are getting the formula TLOH, and only in presence of oxygen here also reaction is possible. Reaction towards air. Now when we are saying air, there is basically presence of oxygen and nitrogen. These two elements we have to consider. Now all the elements in general we are representing it with capital E. E may be any group 13 elements. So there is reaction with oxygen and nitrogen, obviously at high temperature, and especially in case of nitrogen, high temperature is very much important, because when it is nitrogen, there is triple bond present between two nitrogen atoms, and to break this triple bond it requires high energy. So that is why high temperature is required. And when there is reaction with oxygen where E is any element, we are getting this type of oxide E2O3. Now why the formula is so, it is clear, because when it is oxide, it is having -2 oxidation state, and for E it is +3. So 3 into 2 means total positive charge is +6, total negative charge has to be -6. So that is why 3 oxygen, each containing -2 charge. Formula is E2O3, B2O3, L2O3, like this. Then we have reaction with nitrogen. So when there is reaction with nitrogen, this is trioxide and this is nitride. Now look at the formula, nitride En. Now this formula, why it is so? Because nitride anion is nitrogen containing 3 negative charge. So when there is 3 negative charge, to balance this 3 negative charge, this E, that is the element, it may be boron, it may be aluminium. So they are having common oxidation state is +3. So that is why here the formula is like this. So it may be boron nitride, it may be aluminium nitride, like this. Fine. So you should not have any doubt regarding the formula. You just have to know what is the oxidation state of the anion present. So as it is group 13 elements, mostly the oxidation state will be +3. Only in some cases +1 oxidation state is there. But nitride, as it is containing 3 negative charge, so the formula for these group 13 elements when oxidation state is +3 is En. Now Tl, as we know that +1 oxidation state is very important for Tl, so it can also produce Tl2O type of compound. So when it is Tl2O, that means oxidation state is +1, because for each oxide ion the oxidation state is -2. So 2 Tl in +1 oxidation state is required. That is why the formula is Tl2O along with Tl2O3. So this will be formed also, which is following the common oxidation state, as we know for group 13, which is +3. But along with this, there will also be formation of Tl2. Reactivity of these elements increases down the groups as expected. Now boron is unreactive when it is in crystalline form. It is having different types of form. When it is crystalline form, reaction is not there, because to break crystalline form it requires more energy. But if it is not in crystalline form, if it is in finely divided amorphous form, powder form, then reaction is possible, because now the crystal, that is a network type of structure, is not there, so it can easily take part in reaction. Fine. So depending on in what condition boron is present, reaction will be there. And in case of aluminium, there is again this oxide layer problem, as it is mentioned in the previous reactivity discussion also, when that is reactivity towards water. Here also we have seen that oxide layer, when it is not present, then only reaction is possible. Here also the same thing, when aluminium is forming a very thin oxide layer, Al2O3, when it is first in contact with oxygen, just follow the same reaction as it is the general reaction, 4E plus 3O2, just change it to aluminium. Suppose it is 4 aluminium plus 3O2 and you are getting 2 Al2O3. So this is the first reaction. First there will be formation of Al2O3, but once it is formed, instantaneously there will be formation of oxide layer, and as a result, further oxygen gas cannot come in contact with the aluminium surface because of this layer, and this layer is as if acting as protecting layer. So further attack not possible, so ultimately the reaction will stop. So this type of problem is observed with aluminium. Next reaction, how they react with halogens. Now group 30 elements, it is a common reaction, we are representing it. They form this type of trihalide EX3, where oxidation state of E is any group 13 element, it is +3. So they form all type of halides, because we have here different types of halogen, HCl, Br or I, but except TLI3, this is not formed. So with iodide and Tl, there is no reaction. Otherwise, if you consider all the other elements like boron, aluminium, so with boron, it will be Bf3, BCl3, BBr3 like this. Then with aluminium, it will be AlF3, AlCl3. So all these types of trihalide formation possible in presence of different types of halogens, but except TlI3. Next, how they are reacting with different types of acid. Now, when we say acid, first, what type of acid comes in our mind? It is HCl, H2SO4 like this, right? So again, if boron is in crystalline form, there is no reaction with HCl or HF, hydrofluoric acid. So even if you take this acid in boiling condition, that means now you are providing higher energy. You have not taken room temperature HCl or HF. It is boiling HCl or HF. That means temperature is there. So even if we take boiling HCl or HF, then also there is no reaction with boron if it is in crystalline form. But if we take powdered form of boron, now it is oxidized slowly to boric acid. Now oxidation, why we are saying oxidize? Because if you have taken oxidizing acid, now HNO3 and H2SO4, these are examples of oxidizing acid because they also have the capacity to oxidize other compounds. Okay, so oxidize slowly to boric acid. Now boric acid is H3BO3, which is basically a compound of boron, H3BO3. Here oxidation state of boron, it is not 0 obviously. H3BO3, it is +3. So from 0 state, now we are having +3 oxidation state. That means boron has lost electron. So oxidation state from 0 to +3, it is possible because we have taken oxidizing acid such as nitric acid or sulfuric acid. In presence of nitric acid, we are getting H3BO3 along with hydrogen dioxide. And when it is, instead of taking HNO3, if we have taken sulfuric acid, again we are getting H3BO3, but now the byproduct is sulfur dioxide. Why? But remember, it is possible only when it is in powder form, not crystalline. If we consider the other elements except boron, now they can react with both non-oxidizing as well as oxidizing acids, and there is release of hydrogen gas. So now see, the behavior is different. In case of boron, we have not seen any liberation of hydrogen gas, but now hydrogen gas can be liberated. So one example, see, aluminium when reacting with dilute acid, there is liberation of H2, 2 aluminium reacting with 6 HCl, and we have written here, it is actually Al, 2 AlCl3, but if you write it in decomposed state, because it is ionic compound, so if you write it in decomposed state, there will be aluminium 3 plus ion 2 and 3, sorry, total 6 chloride ion. So it is written in this way, 2Al3 plus 6Cl minus. It is actually 2 aluminium chloride along with liberation of hydrogen gas. So aluminium chloride we are getting when the acid is HCl. If it is concentrated HNO3, instead of taking HCl, if we take concentrated HNO3, now there is the problem we have to face, that aluminium becomes passive because of the formation of Al2O3. So in presence of HNO3, now the product is different. Now the product is oxide of aluminium. And because of this formation of oxide, again we know there is protective layer of Al2O3 that will be formed on the surface of aluminium. So first, when you are starting the reaction, HNO3, it is coming in contact with aluminium surface. So first there will be some amount of Al2O3 formation. But this little amount of Al2O3, it will make a protective layer. And further, this HNO3 molecule cannot reach the surface of aluminium. So reaction will be stopped after some time. So the protective layer of Al2O3, why we are saying it protective layer? Because it is not giving the aluminium any opportunity to react with some more HNO3. So it is as if protecting the aluminium, right? So that is why we are saying it protective layer on the surface of the aluminium metal, and there is prevention from further attack. Fine. So this is reactivity towards acid. What about base? Again, the first element resists the action of alkalis when the temperature is up to 773. But if we can increase the temperature further, then there is reaction with potassium hydroxide, and it is forming this type of ion, which we are calling it borate, BO3 3 negative. So this BO3 3 negative, as there is total 3 negative charge, that will, to balance this 3 negative charge, we need 3K plus, 3 potassium plus ion. So that is why the formula is K3BO3, potassium borate. The name of the anion is borate. If the counter ion is potassium, we will call it potassium borate. If it is sodium, it is sodium borate, like this. And temperature, it has to be greater than 773, otherwise reaction not possible. And here hydrogen gas is also liberated. Now some other type of alkali if we take, instead of taking hydroxide type of compound, suppose we have taken sodium carbonate or sodium nitrate, that is, it is mixture actually, not only Na2CO3. It is a fused mixture of sodium carbonate and sodium nitrate, and look at the temperature, it is also very high because it is a first element boron, so mostly we will see high temperature is required. So this mixture of NaNO3 and Na2CO3, which is acting here as the base, now we are getting sodium ion. So now we will get sodium borate. In the previous case, we have obtained potassium borate. Now it is sodium borate. Then there is also formation of NaNO2, sodium nitrite, and carbon dioxide. The next elements, aluminium, gallium. Now there is some amphoteric nature. Okay. Now because of this amphoteric nature, they also react with aqueous alkalis. Why I'm saying it? It is also because in the previous section you have seen that aluminium, it is reacting with acid, and it can also react with base, and there will be evolution of hydrogen. So in both cases, as if just have a look in the previous case, when it is reacting with HCl, there is liberation of H2, and now it is reacting with alkali, aqueous alkali, and there is liberation of H2. But look at the compound, it is NaEOH whole 4 minus, where E is either aluminium or gallium. So either aluminium or gallium. Here it will be NaAlHO whole 4 minus. Actually, when I have written it minus, it is actually plus here to balance it. If you are not writing the positive or negative charge, do not write at all, or write both of them, so that charges can be understood. So EOH whole 4, that means with E there is total 4 HO minus. Now as this E, which is either aluminium or gallium, and here oxidation state is +3, and there is total 4 hydroxide, that means one negative charge will be extra, which is outside this bracket, and to balance this, one Na plus required. So that is why the formula is NaEOH whole 4 minus. So this type of compound we are getting in presence of hydroxide bases, and along with liberation of hydrogen. Indium and helium, however, do not react with alkanes. So there is some variation in properties. It is not that down the group, as we are moving down the group, there will be there is increase in reactivity. It may not be the case always. So in this case, we are seeing here there is no reaction with alkanes. Uses of group 13 elements. Now there is nothing much to discuss, only some points you have to remember, because sometimes there is application related question. So boron has the capacity to absorb neutron, and that is why one of its isotopes, remember in occurrence we have seen two isotopes are there, 10 boron and 11 boron. And among these two, 10 boron is used as moderator in nuclear reactor, because in nuclear reactor the reactions are very fast and sometimes there is liberation of neutrons. And to arrest this or slow down the reaction, 10 boron is used because it has the capacity to absorb neutron, and when neutrons are absorbed, the reactivity, that is there will be some moderation. So that is why we are calling it 10B moderator. There is also some other types of moderators such as heavy water. So 10B is one of these moderators because it has the specific capacity to absorb neutrons. Then amorphous boron as rocket fuel igniter. Some compounds of boron, boric acid, borax. Now these two compounds will be discussed in detail separately. There also you will be able to see some application. So these compounds of boron, boric acid you have already seen the formula, H3BO3. Borax, it is little bit complex. We will also see later separately. So these compounds, they are having some applications such as eye drops, antiseptic, washing powder, different types of glasses, ceramics, bleaches. Okay. Now aluminium, it has so many applications, and all of you, that is some you can also see in our day-to-day life. So everyday life, these are very common. Then in packaging industry to make different types of cans, wrapping materials. Then in construction industries, doors, windows. So as I have said, day-to-day life, we can see the application of aluminium. Transport industries. Then so these are different industries where we use aluminium, and because of its this type of property, both strong and lightweight. So the metal is strong, but it is not heavy. So this is unique property. So we can use its strength in some cases where it is required, but we don't have to face its high weight because it is lightweight. So that is why it is ideal for some architectural application. So it will give the architecture some strength, but as well as it is also lightweight. Then anhydrous Cl3, it is actually acting as Lewis acid. So why it can act as Lewis acid? Because if you look at its all the bonds surrounding aluminium, there is total 3 bonds with chlorine, and in each bond there is 2 electrons. So surrounding aluminium there is total 6 electrons. So it is less than its octet, and as a result it is electron deficient, and because of this deficient nature it will behave as Lewis acid. So and because of this nature it will have some can play some catalytic role where we need some Lewis acid catalyst type of role. For example, Friedel-Crafts reaction, cracking of petroleum. Friedel-Crafts reaction, it is in organic chemistry. So there you will find its application. Then hydrated AlCl3, which is used as mordant in dyeing. Mordant is basically an agent which helps in fixing the dye. So this is the role of AlCl3 in hydrated condition. Gallium, it is used in making semiconductor amplifier, solar cell, tunnel diode. Now you will see some elements of group 13, gallium, and also you will see after that you will also see it for indium. That is semiconducting properties, as you can see. So it is observed for some group 13 elements. It is common for, you can see it for gallium or indium. Gallium is also used in LED lighting, making mirrors. For indium, also making mirrors. Normally in mirror there is application of silver, but the problem with silver is there is tarnishing happening. But if it is made of indium, it will be just behaving just like silver mirror, but tarnishing problem will not be there. And also there are some other roles and uses of the last element, low melting glasses, photoelectric cell switches, production of infrared optics, vermin killer. So vermin is it is a term which is used for there is a common term. So the animals which basically destroy crops, together we call them vermin. So it is used in vermin killer such as rat or mouse poison. that is making those poisons, TL is used. Next, we will consider the separate type of compounds. That is, first here you can see oxide of group 13 elements and also hydroxides. After that, there will be halides and hydrides. So these are common compounds. In case of S block also, we have done the same thing. That is oxide, hydroxide, halides, hydrides. So these are some common type of compounds. Because why we discuss only this? Because mostly any S block or P block, when there will be discussion, you will observe that in chemical properties, we check how they react with oxygen, how they react with nitrogen, how they react with water, how they react with halogens, that is X2. So these are that is the common compounds or elements, reactive elements. So that is why mostly or hydride, that is when they react with hydrogen. So these are some common elements, that is oxygen, nitrogen, halogen, hydrogen, and compound water. So that is why we discuss oxide, which is from oxygen, sometimes compounds of nitrogen also. And because in most cases, reaction with nitrogen directly we will not see, because nitrogen itself is not very reactive. But oxygen, halogen, O2, X2, H2, all these are very reactive. And also when it is hydroxide, that means how they react with H2. So now start from the oxide. Trioxides. Remember the oxides we have seen in today's class only. When they react with oxygen, there is formation of this type of formula. So it is trioxide. Only in case of TL we have seen this formula, which is TL2O, because it is having oxidation state +1, but otherwise mostly it is the formula E2O3, and we are calling it trioxide. Total 3 oxygens are there. So trioxides of group 13 elements, when now they are reacting with water, that is E2O3 reacting with water, we are getting the corresponding hydroxide. So corresponding hydroxide means if you have taken aluminium, it will be aluminium hydroxide. If it is gallium, gallium hydroxide, like this. But look at the formula of hydroxide, it is EOH whole 3 because it is having oxidation state +3. Now the nature of these oxides and hydroxides, obviously it will vary as we are moving down the group. And as we know, there is acidic character, amphoteric character, and basic character. Now basic character we expect when metallic character is maximum. So metallic character increasing means basic character of the oxide and hydroxide, that will also increase, and vice versa. If non-metallic character is increasing, that means acidic character will increase. Though in some cases, that is in between the elements that you will see, there is also some amphoteric type of nature, so they can react with both. So first, if we start from boron, as its oxides and hydroxides, it will be acidic, so that you can expect because it is the least metallic. Then as we are moving down, first we are getting some amphoteric nature. In case of aluminium and gallium, they are hydroxide, they are oxide. And for indium and TL, these two are basic, TL being more basic. So basic character is increasing for hydroxide and oxides as we are moving down the group. In case of boron, it's oxide, E2O3, just replace E with B, and EOH whole 3, just replace E with B again, it will be BOH whole 3. They are weakly acidic in nature, and as a result they dissolve in alkalis, and there will be formation of some metal borate. So we are getting this type of, this is actually sodium metaborate. So when we are saying it is borate, it is actually BO3 3- ion, but NaBO2 it is called metaborate, not exactly borate. Fine. So B2O3 reacting with NaOH, we are getting sodium metaborate and water. Now the next two elements, as they are amphoteric in nature, that is their oxides and hydroxides are amphoteric in nature, and these two are basic in nature. So here we will see equations related to the oxides and hydroxides of aluminium and how they are behaving That is, they are reacting with both acid and alkali, which is the evidence that it is its oxide and hydroxides are amphoteric in nature. If you take the oxide of aluminium, Al2O3, reaction with acid HCl, we are getting LCl3, and when it is reacting with NaOH, we are getting sodium aluminate, NaAlO2, along with water. So these two reaction, it is the proof that it is behaving as amphoteric. Then if you take hydroxide of aluminium, now reaction with HCl, again we are getting same type of salt and water. But when it is AlOH also reacting with NaOH, now see, this is different. So here aluminium with 4 hydroxide, that means 1 negative charge will be extra because aluminium is having +3 and 4 HO minus means 4 negative charge, so 1 negative charge extra, that will be balanced by sodium. So that is why the formula, it is like this. Okay. So oxides and hydroxides of group 13 elements. There is acidic character as we are moving down, basic character is increasing, and also in between these two extremes there is also some amphoteric nature in case of aluminium and gallium. After oxides and hydroxides, halides. So in case of halides, we have seen when they react with halogen, there is all types of EX3 formed except one, which is TLI3. This is not formed, but except that all other types of EX3, it may be LCl3, it may be Bi3. So because E may be any element and X may be any halogen. So trihalides of boron, if we consider specifically the first elements, it's trihalides. If you consider BX3, BX3 means it may be BF3, it may be BCl3, BBr3 or Bi3. Now all of these are monomeric in nature and coordination number is 3. Now if it is mentioned here that it is evident from their low melting point. Now low melting point, it proves that there is not much bonding present surrounding boron. Only 3 bonds. 3 groups are attached to boron. So when we are talking about melting point, high melting point is only there when there is high coordination number or crystal type of structure, because to break all those bonds we need more temperature. But if it is having very simple structure monomer, that is BX3, suppose you have written BF3, so it is very simple. So low melting point. So this is the proof coordination number is low. Now the fluoride and chlorides, that is the first two halogen, it's enhanced if you consider fluorides F minus, chloride Cl minus. Of the heavier members, heavier member means now consider gallium, indium, thallium. Now except this, all are ionic in nature. And now they are having coordination number 6. Now remember boron is the first element, so its behavior obviously it will not be same as the other elements, which is clear from this coordination number. Coordination number is 6 here. Now see, if you consider this picture, here solid state structure of MF3, where M may be any of this element, right? So here if you focus on this violet part, surrounding it, see there is total 6 bonds. So here coordination number is 6. So this central position, and you can see this is there is a network type of structure. So that is why melting point is not low. It is not simple like BX3. So solid structure of MF3, it may be aluminium fluoride, gallium fluoride or indium fluoride. We are having this type of structure. Coordination number is very high. We will also see that for bromides and iodides, except Indian bromide, other bromides and iodides, they are generally dimeric in nature. So here we are talking about Br minus, halide and I minus. The previous statement, it is related to F minus, Cl minus. Now it is Br minus and I minus. They are generally dimeric with coordination number of 4, and there is halide bridging ligands also. So see, here it is solid state structure of MCl3, where M may be any of these, and MBr3. If you are not able to see here, MBr3, where M is India. So indium Br3. So here what we are seeing, they are generally dimeric with a coordination number of 4, which is basically this one. So the last statement that is actually related to this. So see, it is structure of GaCl3 or MBr3, where M is aluminium, gallium, or Tl. So in these 3 structures, there is no mention of boron. It is only for the next heavier elements, and Mi3 also. So bromides and iodides. So here we have MBr3, that is bromide. So this last point is for this structure, and these are iodides. Except Indian bromide, because see, Indian bromide is mentioned here in the second picture, where coordination number, these are actually halogens, that is the green ones, these are actually halogens. Now if you focus on this part, which is basically E, or here as it is mentioned M, you can see total coordination number is 6, as it is mentioned in the second point. Okay, so total coordination number is 6 here. Here also it is 6. It is only 4 here, because here if you look at this M, surrounding M, there is actually total 4 bonds. So that is why it is having coordination number 4, and it is only for bromides and iodides. And you can also expect it, because when it is bromide and iodide, the sizes of these anions are very large. So it is difficult that total 6 anions, 6 I minus or 6 Br minus will be surrounding this M. So that is why it is mentioned like this. So coordination number, it may vary, and only for boron there is simple structure, that is for Bx3, where Bx may be any of these halogen, and it is clear from the low melting point. Some more information regarding the halides. AlCl3, it is unusual. Now why it is so? Because depending on what type of state it is present, that is solid state or vapor state or liquid state, depending on that, you can have different types of structure. So that is why we are saying it is unusual. Sorry. It is in, when it is in solid state, it has ionic structure, cubic, close packed layer type of structure. So as you have seen in the previous slide, here M is mentioned as aluminium, but only for iodide and bromide. Here also we have aluminium. Here also we have aluminium, right? Now this particular statement, it is only for AlCl3. So when it is AlCl3, now you have to consider this picture. AlCl3 M may be Al. So we can have this type of layered structure, cubic close packed layered structure, but that is only in solid state. But when we are heating it, it is readily sublimed, and in the vapor phase and liquid phase, now it will have dimeric type of structure. So whether AlCl3 is present in solid or some other phase, depending on that, different type of structure may be there. And details of this compound, detailed discussion of this compound, that is AlCl3, that will be discussed separately. So I am not going into any further details. Fine. Only look at this picture. When it is solid state structure, you can find this picture in the previous slide also we have seen. But when it is liquid and gas phase, then it is dimer. And if you further increase the temperature, that is very, very high temperature, then only this type of monomeric form is possible. Otherwise, it is dimer in liquid and gas phase. And if it is solid, then there will be crystal type of structure. Okay. So this picture is for AlCl3. This is solid, the first one, then liquid and gas. And the third one is monomer, which is very, very high temperature. Due to small size and high ionization enthalpy, boron can form covalent trihalides. Now, why it is trying to say? Because when you will have ionic compound, then free boron 3 plus must be there. Now, to have this type of B3 plus, you have to provide ionization enthalpy 1 plus ionization enthalpy 2 and ionization enthalpy 3. But these three together are very high. Remember the trend in ionization enthalpy, as you are moving down, it is basically decreasing. So it is maximum for the first element. So as the summation of these three is very high, so this type of cation formation from boron, just like aluminium or gallium, it is not possible. So that is why it will mostly form covalent bond where it will share electron. It is not that it has completely donated electrons and itself is becoming B3 plus, just like ionic bond formation. Remember the basic difference of ionic bond and covalent bond. Covalent bond means there is no such cation formation or anion formation. It is simply sharing of electron. So that is why if you consider any halide, there is sharing of electrons between boron and fluorine. So it is not that boron has given electron, fluorine has accepted. It is covalent bond. It is covalent, forming covalent trihalides, not ionic like aluminium or other elements. Fine. So this is the meaning of this statement. Only covalent trihalides. Now different type of physical state. When it is BF3, it is gas, and as you are moving to higher halogen, that is you are moving from F to Cl or Br, obviously molar mass is now high. Compared to BF3, when you are switching to BCl3, BBr3, molar mass is increasing. So as a result, the physical state is also changing from gas, now it is liquid, and Bi3 is solid. Now the very interesting thing from which question is very common, is all these trihalides, their behavior is Lewis acidic in nature. And what is the order of this Lewis acidic character? It will be gap. Lewis acidic character decreases in this order. So maximum Lewis acidic property you will observe in case of Bi3, and minimum Lewis acidic property you will observe in case of BF3. Now, first of all, you have to understand why all these trihalides of boron are Lewis acid. It is because of its electron deficient nature surrounding boron. There is 3 bonds. In general, I am writing X, and total number of electrons present is 6. So it is not, that is octet is fulfilled. So it will behave as Lewis acid. But why the character is decreasing in this way? To understand that, you have to consider this. So when it is BF3, boron and fluorine both are from same period, both are from second period. So there will be 2 p pi, 2 p pi. Now why we are saying that p pi, p pi? Because see, when it is BX3, just consider this general structure as I have written here. Now this X, which may be fluorine or Cl or Br, there is also some lone pairs present. 3 lone pairs. Now if this lone pair is donated here, there will be some coordination bond. And now the structure will be like this. So one bond is basically coordinate bond. Okay, let me write it as X because I am showing it in general. And as it is donated, sometimes you will also observe it is written like this: B negative, X positive. Now this type of bonding, as the lone pair is bonded towards boron and it is not sharing of electrons. It is completely coming from X, and once it is donated from X, then there is sharing of electrons, and that is the definition of coordination bond, right? Now this is also possible from the other 2X. So the general resonance structure, if I consider, the general structure will be like this. Fine. Now this back bonding when happening, there is actually pi bond formation. This newly generated bond is pi bond, and this bond is between 2p orbital of boron and 2p orbital of, if the X is fluorine, then it is 2p. But when the X is Cl, now it is 3p orbital because chlorine is from not from second period, it is from the next period. Then bromine, the next period. So gradually the p orbital is changing 2p to 3p to 4p to 5p. That means when there is orbital overlap between 2p orbital like this, the size matching is very important. When the size is properly matching, so 2p orbital size matching is proper. As you can see here, the lone pair is donated, it is back bonding. So maximum overlap is possible when there is proper matching of orbital. But as the size is increasing, there will not be proper match. So this sidewise overlap, it will not be very good. And as a result, the bond, there is this type of back bonding, efficiency will be less. So lower is the back bonding. That means the electron deficient nature of boron is still there. There is no proper back bonding. So when back bonding is not good, Lewis acidic character, the electron deficient character is still there. So that is the reason Bi3 is maximum Lewis acidic. Lower the back bonding, higher is the electron deficiency, and as a result, higher will be the Lewis acidity. So this is the reason why Bi3 is maximum Lewis acidic, but as we are moving to lower halogen, this effectivity of pi back bonding is decreasing. So increasing, and as a result, in case of BF3, the electron deficient nature of boron, it is much fulfilled. It is not having any further requirement for electron. So that is why it is the least Lewis acidic in nature. Okay. After halides, hydrides. So hydride means there will be H minus ion, right? Monomeric hydrides are unstable, and even boron cannot form BH3. That means it is true that if you consider their +3 common oxidation state, the formula should be like this, EH3, right? But what happens, this type of monomeric hydrides are not so stable. Even BH3 is not so stable. So BH3 mostly remains in the dimeric form, which is B2H6. And as you are moving from BH3 to LH3, then its stable nature is further decreased. So monomeric hydrides are unstable, and even boron cannot form BH3. It remains, though the formula you can write as BH3 if you consider their oxidation state, but actually it remains in the dimeric form. The stability of the dimeric form of EH3, dimeric form of EH3 means if you take 2, it will be E2H6. So this E2H6, if you consider its stability, decreases steadily down the group. And stability decreasing means what? Reactivity will increase. And why it is so? Because if you consider hydride ion, its size, when you are moving down, the size of the E, that is the size of group 13 element, is increasing. So there will not be much, there will be orbital mismatch. The size of H minus is small. As you are moving down, the size of the group 13 element is increasing. So there is not matching, proper matching. And because of this orbital mismatch, the bonding will be weak. And that means reactivity high. It also means stability is less. So here we can see the structure of B2H6. Though B2H6, it will be discussed separately. So I will not much go into the details of it. And here you can see Al2H6. So this type of, that is individually, there is, the formula should be AlH3, but 2AlH3. Just to remove its electron deficient nature. Just in case of halides, you have seen surrounding the central element, that is central atom, there is 6 electrons. So here also the same thing. To remove that deficiency, it forms this type of bridging bonds. Because if it forms this type of bridging bonds, somehow the electron deficiency to much extent decrease. So here the purpose is to decrease this electron deficient nature, and they remain in the dimeric form. And it is also clear from this bond length, this aluminium hydrogen, which is actual normal covalent bond, normal 2 electrons are present. As we know, any bond, covalent bond, there is 2 electrons. The bond length is 1.575 angstrom, but if you consider this bond, it is longer, 1.740. So it is actually not normal 2C2E bond. 2C2E bond is normal covalent bond as we observe. But in this case, that is not so. So here total 3 center, 1, 2, 3. So this is 3 center, but total number of electrons is basically only 2. So that is why it is 3C2E bond. And same application, same explanation is also here. Here the bond length, if you see, and also this bond is in solid, and this is wedge bond, right? Dotted line. So why it is drawn in such a way? Because if you consider the computer screen, then on the plane of the screen, this part is present, or you can say this part is present. But as if these two BH bonds, they are behind the screen, and these two bonds, they are towards us. Same is also for the second picture. And here the bond length is 131, but this bond is 118. So there is difference between these two bonding. It is not same. And if I write the electrons, somehow you will get the idea how this CC2E bond is formed. So just consider boron, there will be total 3 electrons, right? As we know, valence electrons. And same is also true for this boron. Now see, this hydrogen, it is also giving 1 electron. So now this hydrogen, it has already given 1 electron. So for the lower one, I am drawing this. Now if you see carefully, surrounding this part, there is basically 2 electrons. Similarly, if you consider this one, surrounding this part, there is actually 2 electrons. So that is why it is called 3C2E bond. You can also draw it yourself. So idea will be clear. And 2 different types of bonds are present. Now boron, it has some unique nature because it can form a series of volatile polymeric hydrides. Though that is in general we call them as boron. And the name you can find some analogy with alkane. Remember in organic chemistry when we say alkane, it is carbon hydrogen compound, general formula CnH2n plus 2. Just consider methane. So n value is 1. So 2n means 1, and then there will be 2 more. 2n is 2 and 2 more hydrogen, so total 4. Just like CH4, the next element will be C2H6. So these are alkane. So in alkane, what you see, there is carbon and hydrogen. Now just like alkane, if you consider boron, you can find the similarity in the word. So when it is boron, there will be boron and hydrogen only. So that is why there is some analogy with the alkane. And if we consider silicon, just like carbon, now there will be silicon and hydrogen. So it has some similarity with name, and also because it is compounds with hydrogen only. Now boron is basically separate. There is separate discussion regarding it, which is not in the syllabus, that you will get in higher classes. So boron, where boron forms a series of volatile polymeric hydride. They are having some network type of structure, as you can see here. So though these are very simple, there are also some complex boron. So this is the example, but details not required. Al2H6, as we know, down the group stability decreases. So that means Al2H6, it will be highly reactive, unlike B2H6, and decrease because of this orbital mismatch. B2H6, Al2H6, because of their electron deficiency, they can also react with Lewis bases. So we have already seen that they are electron deficient. That is why they also remain in diameric form, because in diameric form, some electron deficient nature is reduced. And because of the same Lewis acidic character, they can react with Lewis bases. Lewis bases means those compounds which can donate electron pair. It is that there is opposite definition of Lewis acid. So B2H6, you Lewis base, you can consider ammonia, very simple example. So reaction is possible with Lewis bases. It is basically reaction between Lewis acid and Lewis base, and they form adduct. Anomalous behavior of the first element. As we know, the first element boron, its behavior is different, and we already have seen so many examples for that. So boron, so now we will summarize its anomalous properties. It has high boiling point and melting point if you compare with other members, and unlike other elements of the group which are metals, boron is non-metal. Remember, we have seen in case of oxide and hydroxide, it is behaving, its oxide and hydroxides are acidic in nature, and as you are moving down, gradually basic character is increasing. The other elements of the group, they can show covalency beyond 4. But in case of boron, maximum covalent and covalency possible 4. And it is because if you consider its valence shell electronic configuration, 2s and 2p, there is no d orbital. So 2s, 2p, maximum 4 orbitals you are getting for bonding. Even if you are unpairing it, suppose you are transferring this electron here, but this is vacant, but total orbital 4. So this vacant orbital, some compound it can donate, some element it can donate 2 electrons. But whatever it is, 4 orbitals maximum for bonding. Availability is not more than that. So that is why covalency, it is only up to 4. Not more than that. But for other elements, because of presence of vacant d orbital, coordination number can be more. All the elements of the group, they form ionic bonds, whereas boron forms covalent bonds only. Remember, in case of boron, the ionization energy 1 plus ionization energy 2 plus 3. These three are very, very high. And if we want to get ionic bond for boron, there must be presence of B3 plus, which is not possible because of this very high 3 ionization energy. Only when you provide this 3 ionization energy, then only you get B3 plus. But that is difficult to get. So ionic bond is not possible. Only covalent bond, where sharing of electrons are there, but not cation formation. In comparison to other elements, trihalides of boron, they are monomeric in nature. But see in the halide, that slide, halides of group 13, there we have seen different type of structures we have seen for the other members halides, where we have seen some crystal structure, dimeric structure with coordination number 4 or coordination number 6. But in case of boron trihalides, that is BX3, there is no such thing. Fine. When boron trihalides are hydrolyzed, that is you are reacting BX3 with water, then there is formation of tetrahydroxyborate. This one is obtained. So here you can see with boron there is total 4 OH. Not more than that is possible, and overall there is a negative charge. And here this is the maximum coordination it has already reached. But if you consider other members, where E is other member, this general formula EH2 whole 6. Now surrounding E, total 6 water molecules can be present, and it is having 3 plus charge because the oxidation state of E is still 3 plus. Water is neutral, so it has no contribution regarding any negative charge. When it is HO, it has some negative charge. For water, it is not having any charge, it is neutral. So outside it is 3 plus is written because that is the overall charge. It is still 3 plus before the coordination with water. So after hydrolysis for trihalides, we are getting different types of species because of difference in coordination number. For boron, it cannot exceed 4. It is limited up to 4 because of unavailability of d orbital. Okay. So we'll end the session here. Next day, we will see some compounds of boron and aluminium. Thank you for listening. We are ending the session here.